Now that we have seen why machine learning is important, let us begin with a precise definition of machine learning. Machine learning can be defined as the science of enabling computers to learn from data without being explicitly programmed. To understand this definition, we need to break it down. In traditional programming, developers write explicit instructions for every possible situation. For example, imagine writing a program to detect spam emails. You might create rules like if the email contains the word lottery, mark it as spam. If the email contains more than 10 exclamation marks, mark it as spam. Or if the email contains suspicious links, mark it as spam. However, spammers constantly change their tactics. New patterns appear every day. Writing manual rules for all possible spam patterns quickly becomes impossible. Machine learning solves this problem differently. Instead of writing rules manually, we provide the system with a large dataset of emails and labels indicating whether each email is spam or not. The algorithm studies these examples and learns the patterns automatically. After training, the system can classify new emails even if it has never seen them before. Another famous definition of machine learning was given by computer scientist Tom Mitchell, who described it as follows. A computer program is said to learn from experience E with respect to some task T and performance measure P if its performance at task T measured by P improves with experience E. For example, the task is recognizing handwritten digits. Experience is thousands of labeled digit images, and performance is the classification accuracy. As the model sees more data, its accuracy improves. That improvement is what we call learning. Machine learning therefore combines computer science, statistics, optimization, and data analysis to build systems capable of discovering patterns and making intelligent predictions. To better understand how machine works, let us use a simple analogy. Imagine teaching a child to recognize animals. You show the child many pictures. Some pictures are labeled cat, others dog. Over time, the child begins to notice patterns. Cats usually have pointed ears, smaller noses, specific facial structures. Dogs may have different ear shapes, longer snouts, and larger body structures. Eventually, the child becomes capable of recognizing a cat or dog even when seeing a new image for the first time. Machine learning works in a very similar way. The learning process usually follows four main steps. The first step is input data. The machine receives examples, for instance, images of cats and dogs, house price records, or customer purchase histories. That's all. And then the second step is the learning process. An algorithm analyzes the data and tries to discover relationships between variables. For example, if the number of bedrooms increases, house price tends to increase. If a credit card transaction occurs in a foreign country shortly after a local transaction, it may indicate fraud. The third step is model creation. Once the algorithm identifies patterns, it forms a mathematical representation called a model. The model captures the relationships discovered in the data, and the fourth step is prediction. Once trained, the model can make predictions on new unseen data. For example, predicting house prices, detecting spam emails, or recognizing faces in images. This entire process from data to prediction is what we call the machine learning pipeline. One of the most common sources of confusion in modern technology is the difference between artificial intelligence, machine learning, and deep learning. These terms are often used interchangeably, but they represent different levels of hierarchy. Let us understand this relationship step by step. At the top level, we have artificial intelligence or AI. Artificial intelligence refers to the broader goal of creating machines capable of performing tasks that normally require human intelligence. Examples include reasoning, decision making, language understanding, perception, and planning. AI includes many approaches, not just machine learning. For example, early AI systems relied heavily on rule-based systems. Next, we have machine learning, which is a subset of artificial intelligence. Machine learning focuses specifically on algorithms that allow machines to learn from data. Instead of relying on handcrafted rules, machine learning models learn patterns automatically. Most modern AI systems today are powered by machine learning. Finally, we have deep learning, which is a subset of the machine learning. Deep learning uses neural networks with many layers to model extremely complex relationships in data. Deep learning has been responsible for many recent breakthroughs, including image recognition, speech recognition, natural language processing, and generative AI systems like ChatGPT. So, in summary, artificial intelligence is the broader field, machine learning is a subset that learns from data, and deep learning is a specialized subset that uses multi-layer neural networks. Machine learning algorithms can be categorized into three major types. Each type corresponds to a different learning scenario. The first type is supervised learning. In supervised learning, the model is trained using level data. This means that each training example includes both input features and the correct output level. For example, an email classification dataset might contain email text that is spam and some other email text that are not spam. The model learns the mapping from input to output. Common supervised learning tasks include classification and regression. The second type is unsupervised learning. In unsupervised learning, the data does not contain levels. The goal is to discover hidden patterns or structures within the data. Examples include customer segmentation, topic modeling, market basket analysis, etc. The algorithm groups or organizes the data based on similarities. The third type is reinforcement learning. In reinforcement learning, an agent interacts with an environment and learns through trial and error. The agent receives rewards or penalties depending on its actions. Over time, the agent learns a strategy that maximizes long-term rewards. Examples include game playing systems like AlphaGo or robotics control systems or autonomous driving. Now, these three paradigms represent the core approaches used in modern machine learning. Let us examine supervised learning in greater detail. Supervised learning is the most widely used type of machine learning. In this approach, we train models using level datasets. Each example consists of input variables to output level. For instance, student study hours, that output is the exam score. If the input is house features, then the output is house prices. If the input features are patient symptoms, then the output is disease diagnosis. Now the goal is to learn a function that maps inputs to outputs. There are two major categories within supervised learning. The first is regression. Regression problems involve predicting continuous numerical values. Examples include predicting house prices, predicting temperatures, or predicting stock market prices. The second is classification. Classification problems involve predicting discrete categories. Examples include spam versus not spam, or malignant versus benign tumors, or cat versus dog image classification. Several powerful algorithms are commonly used in supervised learning. Examples include linear regression, decision trees, random forest, support vector machines, or neural networks. Supervised learning works extremely well when large amounts of level data are available. Unlike supervised learning, unsupervised learning works with unlabeled data. In many real-world situations, obtaining labeled data can be extremely expensive or time-consuming. For example, labeling medical images requires expert radiologists, or labeling millions of customer transactions require extensive manual work. Unsupervised learning addresses this challenge by discovering patterns automatically. One of the most common unsupervised learning techniques is clustering. Clustering algorithms group data points based on similarity. For example, a retail company may cluster customers into groups such as high-value customers or frequent buyers or occasional shoppers. These clusters help businesses design targeted marketing strategies. Another important unsupervised technique is dimensionality reduction. High-dimensional datasets often contain redundant information. Dimensionality reduction techniques reduce the number of variables while preserving important structures. Examples include principal component analysis, TSNE, or autoencoders. A third unsupervised technique is association rule mining. This technique is widely used in market basket analysis. For example, if customers frequently buy bread and butter together, the system learns this association. Retailers then use these insights to optimize store layouts or recommendation systems. The third major paradigm in machine learning is reinforcement learning. Reinforcement learning is fundamentally different from supervised and unsupervised learning. Instead of learning from level data, an agent learns by interacting with an environment. The learning process involves four key components. The first component is the agent. The agent is the entity that makes decisions. For example, a robot navigating a room, or a chess playing AI, or an autonomous driving system. The second component is the environment. The environment represents the world in which the agent operates. The environment provides feedback to the agent based on its actions. The third component is actions. Actions are the decisions the agent can take. For example, move left, move right, accelerate, or brake. And finally, the fourth component is the reward signal. The environment provides rewards when the agent performs desirable actions. The goal of the agent is to maximize the cumulative reward over time. Reinforcement learning algorithms include Q-learning, SARSA, or deep Q networks. Reinforcement learning has produced some of the most impressive AI achievements so far. For example, DeepMind's AlphaGo defeated world champions in the game of Go. Reinforcement learning is also widely used in robotics, game AI, resource optimization, and autonomous vehicles. By learning through interaction and feedback, reinforcement learning enables machines to master complex sequential decision-making problems. And that's all for this lecture.